friends, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is to discuss about the communication systems ESE Prelims questions of the previous year ESE in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever you upload a new video, the direct notification comes from mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why do waste more time? So let's get started. So now we are going to solve the 111 question. See the question here. A DSB suppressed carrier reception is shown in the below figure if signal to noise ratio is the signal to noise ratio for the direct incoherent detection and SNRS is the signal to noise ratio of the coherent synchronous detection, then what is the relation between the SNRI and SNRS? So basically this is a DSB signal, means there are only two sidebands but the carrier is suppressed. So this is given as the input for this one for band pass filter. So the remaining thing is a coherent detection, means it's a demodulation technique in order to get back the original signal. So basically what is the signal to noise ratio of the input and the signal to noise ratio of the output? That is what he is going to ask in this question. So out of the four options, option B means the signal to noise ratio of the input is equal to signal to noise ratio of the output for this question. So let's solve this numerical. Before I solve this numerical, let me tell a small concept here. See here, this is a message signal M of t and this is a carrier signal C of t. So these two signals have to be multiplied. This is done by the balanced modulator circuit. So by using the balanced modulator circuit means we are going to do the multiplication of the M of t and C of t. So therefore the new signal which you are going to get, which is S of t DSB, it is called to product of the message signal and the carrier signal. So this signal we need to transmit over an antenna. So this is called as a modulation. So therefore here we are going to do the modulation. So now we need, at the receiver we have to do the demodulation in order to get back the original signal, which is M of t. So this is a demodulation circuit. So first thing is, this is S of t DSB. It is, the circuit is placed at the receiver. So S of t DSB is going to come to the receiver circuit with some amount of noise. So W of t is called as some amount of noise which is going to present along with the original signal, which is S of t DSB. And then this band pass filter is going to take only the band of this signal, same thing, the same original signal it is going to pass, means whatever the information present in S of t DSB, same original signal, same is going to pass with the help of band pass filter. So we have to choose the bandwidth of that band pass filters in such a way, so therefore all the signal has to come here also. But here this W of t, the Fourier transform of W of t is going to have W of f. It has a noise free, it has a uniform distribution, means for each and every frequency its values same thing, eta by 2, means the noise is as a constant value for all frequency. So what we are going to do is, by using the bandwidth by band pass filter, we are going to limit only to a few frequency. So therefore this is cut off, only this particular region and this particular region only, that noise is going to pass through this band pass filter. So this is called as the N of t. So some amount of noise is going to pass through band pass filter, so output will have some amount of noise also. So now again this new signal we need to do a coherent detection, which is cos 2 pi fct. We have to multiply for this signal and also for the N of t, some amount of noise, and then we have to pass through low pass filter. Then we are going to get the output. That output is y of t, and some amount of noise is also going to present at the output. So basically the noise is going to present at each and every step, but only thing is the quantity is going to get reduced. So but here the initially the rate of noise is W of t, and later here the noise is N of t, and finally the output signal some amount of noise is there, which is P of t. So in the question they are asking what is the signal to noise ratio at the input and signal to noise ratio at the output. So input signal is S of t DSB and the input noise is W of t, and the output signal is y of t and the output noise is p of t. So basically we have to find what is the signal to noise ratio in the input and signal to noise ratio of the output. So this S of t DSB is equal to M of t into C of t, which is the product of the message signal and the carrier signal. So C of t is equal basically Vc into cos 2 pi fct. So M of t into Vc into cos 2 pi fct. See, suppose if M of t is going to have a power Pm, see this message signal is going to have some power Pm, then carrier power, the carrier signal will have power, which is RMS value of the voltage whole square. So RMS value of the signal is Vc by root 2 whole square. RMS, we have to take the RMS value of the signal and then we have to do the square of that. So RMS of Vc cos 2 pi fct is Vc by root 2, and then we have to do the square of that one. So now this S of DSB is a product of the M of t and C of t. So whenever we are going to multiply the two signals, then this signal will have a power which is the product of the individual signal power. So therefore here this S of t DSB is nothing but this is the SI. SI is called as the input power, input signal power which is going to present in the S of t DSB. See, whatever the power which is present in this signal S of t DSB is called as the SI. So it is a product of the M of t and C of t. So therefore this signal will have a power which is a product of the individual powers. So M of t will have power PM and C of t will have power VC by root 2 whole square. So we have to do the product because the signals are multiplied, so the individual powers are also multiplied in order to get the signal power. So therefore if you do this calculation, we are going to get VC square by 2 PM. So we have figured out what is the amount of power which is present in this S of t DSB. So now we need to find what is the amount of power which is present in the noise. So noise with respect to frequency waveform we have already seen. So now how much amount of power which is present in this signal we need to figure out, which is noise power. I have already told you in the previous lecture itself only, the noise power relation is K into T into B, where B is called as a bandwidth. Here we are going to take the message signal. M of t has a bandwidth of W. So therefore instead of B I am going to replace B by W because I am going to choose that message signal. The message signal, let me assume this is the message signal M of F, which has a bandwidth of W and minus W. So therefore the bandwidth of this message signal is only W. So therefore instead of B I am going to replace B by W. So therefore KT into W. So I am going to assume KT is equal to eta for a convenience. So therefore eta into W. So for the input I know what is the input power in the signal and also input power in the noise. So I need to find what is the signal to noise ratio, means signal power by the noise power. So therefore VC square by 2 PM, if you divide by eta W, this is the relation we are going to know because we know the value of SA and we know the value of NI. Substitute these two values and do the division and this is what we are going to get. So finally signal to noise ratio of the input is VC square PM by 2 eta W. So now we need to find what is the signal to noise ratio of the output. So I have already told you by using the band pass filter the same S of DSB is going to pass through the output also, but only thing is by using the band pass filter only we are going to limit the range of frequencies of the noise. So again we are going to do the coherent detection, means cos 2 pi FCT we have to multiply by cos 2 pi FCT for S of t DSB and for N of t DSB also we have to do, and then we are going to get some here Q of t. Let me assume this, the Q of t is some amount of noise, and then this X of t is nothing but S of t DSB into cos 2 pi FCT. So X of t is equal to S of t DSB into cos 2 pi FCT. But if you want what is the noise Q of t is equal to N of t into cos 2 pi FCT. So therefore X of t is equal to S of t DSB into cos 2 pi FCT. So S of t we know which is M of t into C of t. C of t is VC cos 2 pi FCT into cos 2 pi FCT. So basically now I am going to take VC as outside. So VC into M of t into cos 2 pi FCT, and cos 2 pi FCT is cos 2 pi FCT whole square. So cos square theta. So basically cos 2 theta is equal to 2 cos square theta minus 1. So therefore cos square theta is equal to cos 2 theta plus 1 by 2. So by using that relation I am going to get finally this one. So this is the X of t. So by using the low pass filter I am going to remove this term. Only this term I need. So therefore Y of t is equal to VC by 2 M of t. So I need to choose the cutoff frequency of the low pass filter in such a way in order to remove this second term and the only first term I need. So therefore Y of t is equal to Vc by 2 M of t. So if you see carefully, the output is a sum directly proportional to M of t. So it's a scalar multiple of the M of t. So the demodulation main principle is same thing. So by using the modulation we have got the S of t DSB. By using the demodulation we need to get the same original signal, message signal, which is Vc by 2 M of t. Yes, we have got this one. But still with this signal there will be small amount of noise. So here Q of t is equal to, so similarly Q of t is equal to N of t into cos 2 pi FCT, and then we have to pass this signal Q of t through a low pass filter. Then we are going to get some signal P of t. So finally I am going to draw the Fourier transform of this frequency range of this noise. So output will have some amount of noise which is P of f, which has a value of eta by 4 for range of minus W to plus W. So in this range of minus W to plus W, this noise waveform, frequency waveform is eta by 4, and remaining all other ranges its value is 0. So now I want to know what is the signal power in the Y of t and the noise power in the P of t. So basically now signal power in the output signal. So Y of t, this is the waveform. Y of t expression is Vc by 2 into M of t. So I want to know what is the power in this signal Y of t. So basically suppose if X of t has a power P, then k into x of t. So if you are doing the scalar multiple of the previous signal, then the new power will be k square times the pm. So that scalar you have to do the square, and the pm you have to take the original one. So therefore, if any new signal is a scalar multiple of the previous signal, then its power will be k square times the pm. So m of t has a power pm. So therefore, Vc by 2 is scalar. So you have to do the square of that one. So therefore, this signal y of t has a power which is scalar square. So therefore, scalar is Vc by 2 whole square pm. So therefore, if any signal, if you are going to do the scalar multiple, then that signal will have a power which is scalar square times that signal power. So therefore, Vc by 2 whole square times pm, which is Vc square by 4 pm. So this much amount of power which is present in the y of t. I want to know what is the amount of power which is present in the p of t. This is the noise power. So this is the waveform we know, which is P of f with respect to frequency minus W2 plus W. So area under this curve is nothing but noise power. So that this much amount of noise power is going to present in this P of t. So I want to know what is the area of the signal. So area is this, width is 2W and the height is eta by 4. So therefore we are going to get now eta in W by 2. 2W into eta by 4, we are going to get W eta by 2. So this much amount of noise power which is going to present in the P of t signal. So now I need to find what is the signal to noise ratio. Signal to noise ratio is S0 by N0. So we know the value of S0 and we know the value of N0. So substitute them and do the calculation. So we are going to get Vc square Pm by 2 eta W. So in the question they are asking what is the signal to noise ratio of the input and signal to noise ratio of the output, and then correlate them. So if you see carefully, signal to noise ratio of the input and signal to noise ratio of the output, both the expressions are same. So therefore we can say signal to noise ratio of the input is equal to signal to noise ratio of the output. So finally what I am trying to say is very simple. By using the modulation technique, we are going to produce the S of t DSP. So then it will have some amount of noise. So this noise is going to get changed. As the noise is going to pass through all the systems, the noise is going to reduce and finally it is going to come in this range only. But initially it is for all frequencies the noise is going to present. But finally in the output, only for a bandwidth of minus W to plus W, only it has a eta by 4 and remaining all other initial it is 0. So along with the signal, the noise is also going to present but in a very small quantity. So now I need to find what is the signal to noise ratio in the both cases, and I need to equate them whether they are equal or not. So but in this case they both are equal. So now we are going to solve the 112 question. See the question here. The detection gain for current DSB demodulator. So the previous question only. So for the previous circuit itself. So now we need to find what is the detection gain for the current DSB demodulator. We need to figure out. So what are the four options? Option A 2 is the correct solution of this question. So let's solve this question. So now we are going to see about this question. See, listen carefully. So same thing I am going to repeat, but I am going to tell you now in detail graphs also. Listen carefully. Suppose this is a DSB transmitter. So DSB transmitter is nothing but here it is, this circuit is going to the multiplication of the message signal and the carrier signal. So therefore S of t DSB. So basically S of t DSB is equal to M of t into C of t. So this signal is going to send to the transmitter. So it is going to send to the transmitter. So this is called as a modulation technique. So at the transmitter. So now I want to keep a demodulation circuit at the receiver in order to get back the same signal M of t. So this DSB, S of DSB is going to pass through in the air, but due to in the channel, because some amount of noise is going to present, so therefore this noise is going to represent by the, which is W of t. So W of t is going to represent that noise, and S of DSB is the multiplication of the M of t and the C of t. Actually we need only S of DSB, but due to noise present in the atmosphere, this is a signal W of t. So it is going to pass through a band pass filter. So see here, suppose let me assume the frequency response. This is a frequency response. Let me assume that message signal frequency is going to have this minus W to plus W. So W is the bandwidth of this message signal. So S of f DSB, I want to know what is the Fourier transform. So therefore, if you know this one is S of DSB is called M of t into C of t. So if you take the Fourier transform, it is product in the time domain will become convolution in the frequency domain. So by using the convolution, finally we are going to get this waveform. So therefore, the cutoff frequency is Fc. So this is the Fc is the carrier frequency of the signal. So therefore this is the Fc. So same waveform, but we have to shift here. So therefore Fc plus W and Fc minus W, and same thing here also. This is minus Fc. And now I am going to for the noise W of t. So for the noise W of t, the frequency domain representation is eta by 2 for all frequencies. For all frequencies, it is going to have eta by 2. And now here, this is S of t. See, suppose This we know the value of S of t DSB and we know the value of the W of a frequency domain. So it is going to pass through a band pass filter. So I am going to choose a band pass filter in such a way. So this is a band pass filter. I am going to place a band pass like filter like this. And here also same band pass filter. So these two signals are going to pass through this band pass filter. So therefore the bandwidth of this band pass filter is here Fc plus W and here Fc minus W. And similarly here also minus of Fc minus W and here minus of Fc plus W. So only whatever the signals which are going to present in this range only, that signals are going to pass. So therefore this whole signal and this whole signal are going to pass through the band pass filter. So therefore now here we are going to get the same thing, S of the DSB. So this is the output of the band pass filter. So same thing I have written, S of the DSB, the frequency domain is S of F DSB. Now N of t, some amount of noise is going to pass through this band pass filter. So I want to know what is the frequency domain representation, which is N of F. So this is W of F. When I keep the band pass filter, only these range of frequencies are going to pass, which has a value of eta by 2 peak value. So therefore eta by 2, only these range of frequencies of the noise are going to pass through the band pass filter. And then I am going to place this coherent detector. This circuit is called as a coherent detector. Basically this is a coherent detector. So X of t is equal to S of the DSB into cos 2 pi FCT, and similarly some amount of noise is going to pass, which is N of t into cos 2 pi FCT, and then these two signals are going to pass through low pass filter. Through X we are going to get the output Y. So just now in the previous example only I wrote the expression Y of t is equal to half into M of t. So if I know what is the Fourier transform of the frequency domain of the Y of F, this is what I am going to get. Same thing, but as some scalar multiple of the message signal I am going to get here. So that is the principle of demodulation. We have to get back the same original message signal. But there is some small amount of noise is also going to present. So I want to know what is the frequency domain representation of this noise. P of t is a small amount of noise is going to present in the output. So P of F representation is eta by 4 with minus W2 plus W. So therefore this is the frequency domain range. So now I want to know what is the coherent detection gain. Coherent detection gain is nothing but this is a coherent detector. So for this coherent detector, the input is S of t DSB, and also the noise input is N of t, and the output is Y of t, and output noise is P of t. So here we have to find what is the signal to noise ratio of the output by signal to noise ratio of the input of this detector, not overall circuit. If you want to figure out what is the overall circuit, then the output is Y of t and then noise output noise is P of t, and the input is S of t DSB and the noise input is W of t. But here we have to do the coherent detection only for the coherent detector circuit, only gain for the coherent detector circuit. Only these two is called as a coherent detector circuit. So therefore the output is Y of t and P of t, and the input is S of t DSB and N of t. So now we have to find what is a coherent detection gain. It is a signal to noise ratio of the output of detector. Output of signal is Y of t and the noise is P of t, and signal to noise ratio input of detector, signal is S of t DSB and the noise is N of t. So we have to figure out that one. So basically I have already told you the output signal is Y of t, which is VC by 2. So this is VC by 2. So VC by 2 into M of t. So therefore whatever the power in this signal S of, so whatever the power present in this Y of t is equal to S naught, which is represented as VC by 2 whole square into PM. Just now I told in the previous example itself, which is VC by 2 whole square into PM, which is VC square by 4 PM. So this much amount of power is going to present in the signal Y of t, and then there is a noise P of t. So the noise is going to have how much amount of power. So noise, how much amount of power is going to present. So I have already told you the graph, which is PF from minus W to plus W have a value of eta by 4. So therefore if you want to know what is the noise power, you have to figure out what is the area of this graph, which is 2W, which is 2W, base is 2W and height is eta by 4. So basically it is going to get eta W by 2. So same thing, 2W into eta by 4, so eta W by 2. So now I want to know what is the signal to noise ratio output of detector is S naught by N naught. So we know the value of S naught and we know the value of N naught. Substitute them. Finally we are going to get VC square PM by 2 eta W. And now we need to find what is the signal to noise ratio of input of the detector. So for the input of detector, the input is S of t DSB. It is a signal, and the noise signal input signal is N of t. So I want to find what is the power in the S of t DSB and also power in the N of t. So basically signal to noise ratio of input of detector is equal to the signal power which is present in the S of t DSB and the noise power which is present in the N of t. So signal power. So signal power S of t is nothing but here I have already told in the previous example only. S of t DSB is equal to M of t into C of t. So C of t is called as a VC cos 2 pi FCT. So here Suppose form of t, the power is Pm. And so Vc cos 2 pi ft, the power is RMS value whole square. So Vc by root 2 whole square. So when we are going to multiply these two signals, the power also she must multiply. So therefore, this S of dsb will have power which is Pm into Vc by root 2 whole square, which is Pm Vc square by 2. So same thing. Pm Vc square by 2. And similarly, Ni is called as the noise power which is present in the signal n of t. So I want to know what is the frequency domain. So for the frequency domain representation n of f, only these range of frequencies are going to pass through the band pass filter. So I want to know what is the noise power present in this n of f, which is area. So this area is area of this graph, which is with this 2w, and this is eta by 2. And similarly here also 2w, and this is eta by 2. So you have to find what is the area of this one and area of this one. So area under the frequency domain graph is going to tell you how much amount of power which is present. So therefore 2w into eta by 2, and here also same thing. So directly you have to do the multiplication. Same thing, also 2w into eta by 2 plus 2w into eta by 2. So simply we can say 2w into eta by 2 into 2. So 2 get cancels. So finally 2w eta is the power which is present in the n of f. So therefore 2 into eta by 2 into 2w. So same thing we will get here. So now do the division. Finally we are going to get Vc square Pm by 4 eta w. So we figure out what is the signal to noise ratio of the output of detector and signal to noise ratio of the input of detector. So now we need to do the division of these two things. Signal to noise ratio of output of detector to signal to noise ratio of input of detector. And if you divide them, we are going to get coherent detection gain, which is value 2. So this is the correct solution of this question. So what I am trying to say is simply, this is a coherent detector circuit. So the output is y of t and the output noise is p of t. So we have to find what is the power in the y of t and the power in the p of t. And similarly, the input to the detector is s of t dsb and the n of t. N of t is a noise. So we have to find what is the power present in the s of t dsb and the power present in the n of t. And then we have to do the ratio, signal to noise ratio of output of detector by signal to noise ratio of the input of detector. Then we are going to get the coherent detector gain. So if you want to find what is the coherent for this overall gain is nothing but signal to noise ratio of the output by signal to noise ratio of the input. So now you are going to solve the 113 question. See the question here. A pre-emphasis circuit provides extra noise sensitivity by. So a pre-emphasis circuit, it is going to provide the extra noise sensitivity by, out of the four options, option B, amplifying the higher audio frequencies. So here we'll discuss more about this one. So this is the power spectral density of the message signal. The graph is going to look in this manner, and similarly the power spectral density of the output noise, it is going to look in this manner. So as the frequency increases, as we are going to increase the frequency, the power spectral density of the message signal goes on decreases. Whereas as the frequency increases, the power spectral density of the output noise goes on increases. Means the output is going to have the highest power when compared to the message signal whenever the frequency increases. So therefore we can say signal to noise ratio. So therefore the signal power is going to decrease, whereas the noise power is going to increase at the highest frequency. So therefore output is going to have more effect of the noise. So but we want only the message signal. So at high frequency the noise effect is very higher when compared to the signal. So therefore the output is going to have more amount of noise. So what we are going to do is, in order to avoid this one, at high frequencies, whenever at high frequencies we are going to increase the amplitude of the message signal. So whenever we are going to increase the amplitude of the message signal, means the signal power is going to, we are going to increase higher and higher and higher. So therefore now here, so therefore finally anything higher by anything smaller higher is going to, again you are going to get the signal. So therefore here at high frequencies we are going to increase the amplitude of the signal. So therefore the power of the signal is going to increase higher when compared to the noise. So therefore the output we are going to get the signal rather than the noise. So that is what we are going to do with the help of the pre-emphasis circuit. So before we transmit the signal, we are going to keep a pre-emphasis circuit. So the main aim of the circuit is nothing but here, it is going to increase the signal amplitude for high frequencies. So it is going to increase the amplitude of the signal at high frequencies. So at high frequencies the signal amplitude is increases, means the power is going to increase higher of the signal when compared to noise. So output we are going to get the same thing, which is the message signal. So similarly same thing here at the receiver. This is pre-emphasis circuit we have to do at the receiving, at the transmitting side, and then at the receiver side we have to keep a de-emphasis circuit. So by using the de-emphasis circuit you have to do the reverse process of the pre-emphasis circuit. Means at high frequencies now we are going to reduce the higher amplitude of the signal. So therefore finally we are going to get the message signal. So here what I am trying to finally say is, so whatever the signal we are going to transmit here, it is going to have the highest signal power when compared to the noise. So therefore here always we are going to get the signal rather than the noise. So further the signal is going to receive at the same signal is going to receive at the receiver, otherwise the noise, only the noise power is going to receive at the signal. So that is what we are going to do. So in the transmitting side we have to keep a pre-emphasis circuit, and at the receiving side we have to keep a de-emphasis circuit. So now we are going to solve the 114 question. See the question here: which one of the following modulation techniques has got maximum signal to noise ratio? So which of the modulation techniques are going to have the highest signal to noise ratio? So option A, AM single sideband; option B, AM JSB; option C, FM; option D, AM SE suppressed carrier. So therefore out of the four options, option C, FM is the correct solution of this question. So let's solve this numerical. So figure of merit is also called as the signal to noise ratio. So therefore now I am going to calculate what is the figure of merit for the FM, for the PM and for the AM. So these are the expressions of the figure of merit for the FM, PM and AM, which is 3/2 beta square, 1/2 beta p square, and m square by 2 plus m square. So here beta is called as the modulation index of the FM, and beta p is the modulation index of the PM, and m is the modulation index of the AM. So here beta p is going to lie between 0 to 1, and similarly beta is going to lie between 0 to 1, and similarly m also 0 to 1. So now I want to know which one is going to have the highest value. So let me assume beta, all these things are assumed to be 1. Suppose let me assume the maximum value, beta is equal to beta p is equal to 1, and I am going to see which one is going to give the highest value. So when all these things are equal to 1, means beta is equal to 1, we are going to get 3/2, which is 1.5. And similarly here, if I substitute 1, which is 1/2, which is 0.5, and here which is 1/2 plus 1 square, which is 1/3. 1/3 is 0.33. So we can conclude that this 1.5 is highest when compared to remaining two things. So therefore figure of merit of FM or signal to noise ratio for FM is more when compared to the remaining things. So therefore this is the very highest value. So FM is going to have the highest signal to noise ratio or figure of merit when compared to remaining modulation schemes. So now we are going to solve the 115 question. See the question here: match list 1 system with the list 2 application and select the correct answer. So list 1 is about the different systems and what are their applications. So list 1, pre-emphasis, Armstrong method, envelope detector and de-emphasis. And similarly the list 2 is AM detector, FM receiver, FM generator, and 4th is FM transmitter, and the 5th is AM transmitter. So what are the four options? Option D is the correct solution of this question. So let's solve this question. So in the previous example only I have told you about the importance of the pre-emphasis circuit and the de-emphasis circuit. So basically the pre-emphasis circuit is kept at the sending side, means at the transmitter side, because at high frequency the power spectral density of the noise is very higher when compared to the power spectral density of the message signal. So power spectral density of the noise is very higher than the power spectral density of the signal. So therefore what is going to happen now at that condition? Signal to noise ratio. So therefore here the signal power is very lesser when compared to the noise power. So therefore we are going to get a low value of the signal to noise ratio. So because of this, the output, the signal, whatever the output is going to receive at the receiver, will have more amount of noise when compared to the signal. So therefore what we have to do, then we have to increase the signal power. So in order to increase the signal power at high frequencies, because at high frequencies the amplitude of the message signal is going to decrease. So because of that the power is going to decrease, so signal to noise ratio is also going to decrease. So here we have to keep a circuit in such a way at high frequencies the amplitude value we have to increase. So whenever we are going to increase the higher amplitudes at higher frequency, then the power is also going to increase. So as signal to power noise ratio, as signal is going to increase and increase, so therefore now signal to noise ratio is going on increases, means the signal will have highest power when compared to the noise. So therefore now whatever the signal it is going to receive at the receiver will have more amount of the signal rather than the noise. So signal will have higher power when compared to the noise. And similarly at the receiver side we have to do the reverse process of this one, so in order to get the pure message signal. So therefore whatever the output, by using the demodulation technique we have to make the same as a message signal. So therefore here we have did in this, we did a extra amplitude of the message signal. signal at higher frequencies. So therefore we have to do the reverse process. So whatever the signal strength at higher frequencies, now we have to decrease those amplitudes at higher frequency, and then we have to pass through demodulator, then we are going to get the message signal. So all this pre-amplifier circuit and DMC circuit are we are going to do in the FM, because in order to make this as a signal to noise ratio as higher value. So therefore we can say this pre-emphasis circuit is kept at the FM transmitter and the de-emphasis circuit is kept at the FM receiver. And similarly envelope detector, this is going to make it as a AM detector, because we have already told you in the demodulation technique we are going to use the envelope detector. So by using the envelope detector, this detector is going to function only for M, the modulation index less than or equal to 1. So if it is more than 1, there is a distortion in the S of t AM. So therefore we can't get back the original message signal no matter whatever you do. So therefore always we have to keep M less than or equal to 1, because this envelope detector is going to use in the AM demodulation. So therefore it is used as a AM detector. And similarly, if you want to generate the FM signal, there is a one method which is called as the Armstrong method. So by using the Armstrong method, we can generate the FM signal. So these are all the things about this one. This is a systems and their applications. So now we are going to solve the 116 question. See the question here. Match list to an FM service type and list to channel bandwidth and select the correct answer using the codes given below. So the list one is going to contain about the FM service type and what is the bandwidth required for this one. So for each and every application. So therefore out of the 4 options, option C is the correct solution of this question. So let's solve this question. So all these are going to belong to the FM service time and the respective channel bandwidth. So this FM modulation was first, it was invented by the Edwin Armstrong. So Edwin Armstrong was the first person who invented this FM modulation, and it is better than the AM modulation. So therefore here the signal to noise ratio of the FM is also more than the remaining all other modulation schemes of analog. So therefore we can tell that here for commercial FM radio broadcast means you can see, so presently there are so many radio channels are going to there for commercial use, they are going to broadcast their signals. So each channel is going to have a bandwidth of 200 kilohertz. So we can say which is 0.2 megahertz. Suppose 98.3 FM. So therefore megahertz, that will have a bandwidth of only 0.2 megahertz. And similarly, suppose 93.5 megahertz and 94.2 megahertz. So therefore all these are the radio channels. So for each channel will have a bandwidth of nearly 0.2 megahertz by using this FM transmission. So therefore 0.2 megahertz is the bandwidth for each and every channel in the FM broadcast. And for television sound, the bandwidth is 100 kilohertz. And for police, but that police means that in the police vehicle there will be some sound, right? That which called as a police, fire and ambulance. All this is going to make some sounds. That will have a channel width of 20 kilohertz. And similarly amateur radio is nothing but is also called as a ham radio. It means suppose one person is wanting to make a radio for his own self, so for experimental purpose. So therefore that is called as an amateur radio. So it can go only up the channel width of only 15 kilohertz. So as the frequency increases, the distance covered by that signal is also going to increase. So therefore here amateur radio is only for individual persons or some company for their own communication. So it is called as a amateur radio or the ham radio. For experimental purpose we are going to use this by individual or for any company. So it is only 15 kilohertz. So therefore we can see out of all these things the least is the amateur radio or FM ham radio, means only for a single person or a single community or a single company. So it is a very less. And the highest is FM radio broadcast. So because of this only we are going to listen the channels in our phone. So therefore this is called as a radio. So highest broadcast frequency channel bandwidth is 0.2 megahertz and remaining things are very lower. So now we are going to solve the 117 question. See the question here. The maximum number of contrast amplitude levels in a 3-digit ternary PCM pulse code modulation system can be used to represent this. So here basically in the pulse correlation modulation we are going to use a 3-bit at the output. So with the help of this, how many levels we can get, means contrast levels, how many maximum contrast levels we can get. So out of the 4 options, option A is the correct solution of this question. So let's solve this numerical. So PCM is a digital communication. So pulse code modulation, so it is a digital communication. So with the help of digits we are going to represent that sample. So therefore the number of standard contrast levels less than or equal to 2 to the power of n. So therefore L is called as the number of standard levels of standard amplitude, means a fixed amplitudes, how many fixed amplitudes we can keep. Otherwise the signal will have large amount of number of infinity of amplitudes if you do the sampling. But by using this quantization we are going to represent the standard levels. Suppose the standard level is 5 volt. Suppose if the standard level is 5 volt and if any signal which has 5.2, then it is going to assumed as 5 volt with the help of this quantization, because we are going to assume this 5.2 as a 5 volt with the help of quantization. So therefore the n is called as the number of binary bits. So with the help of this binary bits we are going to send the or transmit this signal. So therefore here in the question they have given n is equal to 3. So therefore if you substitute here n is equal to 3, n less than or equal to the power of 3. So 2 to the power of 3 is 8. So maximum levels you can keep with the help of this 3 bit is 8. Only 8 levels you can keep in the PCM, standard amplitude levels. So 8 is the correct solution of this question. So now we are going to solve the 118 question. See the question here. Which one of the following statements is correct? Quantization noise is produced in. So out of the 4 options, quantization noise is going to produce only in the PCM, pulse code modulation, because quantization noise is equal to quantized value minus sample value, or we can say which is sample value minus quantized value. So with the help of this only we are going to get the quantization, because quantization is the only principle which is going to use only in the PCM. So therefore because of this quantization we are going to get the quantization noise. So let's discuss something more about this one. So basically this is a block diagram of a PCM transmitter, pulse code modulation, which is a digital modulation. So noise effect is very higher, noise immunity is very higher in the PCM regarding any other communication schemes. So therefore here M of it is a message signal. So we are going to use a sampler, means we are going to use a sampler, means we are going to get a discrete signal like this, a varying amplitudes. So discrete type signals of infinite amplitudes we are going to get the output of this sampler. So because of this there are infinite number of amplitudes we can get for any time duration. So because of this we are going to use a quantizer, because we are going to fix them. We are going to fix the amplitudes to a certain levels. Instead of getting infinite number of amplitudes, we can now get a finite number of amplitudes. So we can approximate this signal to that quantizer. So because of the quantizer we are going to approximate the amplitude to a standard levels. So then the standard levels means we are going to get in this fashion. So like this is a fixed amplitude. Suppose this is 5.2, let me assume this is the standard is 5.0. So 5.2 is approximated as 5.0. Suppose this 5.26, then is approximated, still it is approximated as a 5.0 only. So because we are going to use a quantization, means we are going to use standard. So therefore with the help of this we are going to get a fixed amplitudes. So now we are going to encode this signal. So whatever the signal of the quantizer, we are going to encode with the help of encoder, means we are going to convert into a digital format with the help of n-bit binary. So encoder is going to convert the analog signal into a digital signal. So therefore here by using the encoder we are going to represent each and every sample. So this is the sample, sample 2 and sample 3. Each sample we are going to represent with the help of a n-bit binary. So therefore now I am going to assume that n is equal to 3. It's a 3-bit binary. So 1, 2, 3. So with the help of 3 bits we can get 000, 001, 010, 011, 100, 101, 110 and 111. So therefore 8 levels we can get. So with the help of 8 levels we can give an output of quantization, means standard levels we can fix. Let me assume the standard levels are 0, 0.5, 1, 1.5, 2, 2.5, 3.0 and 3.5. So these are the standard levels. So here suppose let me assume this output of the sample. So output of the sample are sample value. So these are the actual amplitude values after the sampler. So now these are the standard levels. These are the standard levels. So therefore now what we are going to do is the quantization error is equal to actual sample value minus the quantized value. But actually we need a sample signal, but we are going to approximate with the help of quantizer in order to get a finite number of amplitudes. And if you do the subtraction, sample value minus quantized value, we are going to get this range. So therefore we can say this quantization error is only, it is going to present only in the PCM, because here we are going to use a quantizer. Because of this quantizer only we are going to get the quantization error. So the maximum number of levels, so maximum number of levels can be 2 to the power of n. So it's up to you whether you can use the whether 6 standard levels or 4 standard levels, is up to you, but the maximum number of levels you can keep is only 2 to the power of n, which is 2 to the power of n. So therefore number of bits. So this is all about this one. So in the pulse code modulation there will be a quantization error because of the quantizer. So the above circuit is just now I discussed, which is the PCM transmitter. So now the below circuit is the PCM receiver. So this is a PCM receiver, means at the receiver this is the circuit of the PCM. So therefore here is a digital signal. So the digital signal is going to send at the receiver. So same receiver signal is a digital format. So now we are going to keep a regenerative. So because of this still it is a binary data, means a reverse of that process, quantization. So therefore now by using the decoder we are going to convert into a analog amplitude value, and then by using the low pass filter we are going to get the pure message signal. So here PCM, so every scheme is all about the modulation and demodulation in order to get back the same original modulation schemes, same original message signal scheme. So therefore this is the PCM receiver circuit, and the above is a PCM transmitter circuit. So it is a digital modulation here. This PCM belongs to digital communication method, PCM transmitter, and this is a PCM receiver. So now we are going to solve the 118 question. See the question here. So analog data having highest harmonic at 30 kilohertz. So highest harmonic at 30 kilohertz means maximum frequency is 30 kilohertz. The message signal has highest frequency of 30 kilohertz. Generated by a sensor has been digitized using 6 level PCM. So the number of bits which are used in the PCM is only 6 levels. Means 6 channel levels. Then what will be the rate of digital signal generated? Means the bit rate, means how many bits per second we are going to generate with the help of these things. So what are the 4 options? Option D, 180 kbps, kilobits per second is the correct solution of this question. So let's solve this numerical. So in the question, this is a PCM transmitter, pulse code modulation transmitter. So it is a sampler. So here we are going to use a sampling frequency Fs. So with the help of this one, we are going to sample this message signal M of t, and then we are going to use a quantizer and then encoder, and then we are going to transmit the signal in terms of the n-bit binary. So therefore here in the question they are given a M of t. This M of t signal will have a maximum message signal frequency of 30 kilohertz. So therefore here in the question they are also given that the number of levels which are used in this quantizer, the number of channel levels which are used in this quantizer is 6 levels, 6 channel levels. But we know that the number of levels can be less than or equal to 2 to the power of n. In the question the number of levels is 6. So less than or equal to the power of n. Suppose if n is equal to 1, then only 2 levels are going to produce. If n is equal to 2, we are going to produce the standard levels which are the 4 levels, which 2 square is 4. And when n is equal to 3, we are going to get the standard levels is 8. So therefore the 6 is going to lie between the 4 and 8. So therefore minimum 8 levels are required. So minimum 6 levels are represented. So therefore 6 levels are going to lie between the 4 levels and 8 levels. So therefore minimum 3 bits are necessary. So therefore the minimum 3 bits are necessary in order to represent the 6 levels. So therefore here we have to do a sampling frequency. Already I have told you the sampling frequency must be twice the maximum frequency, then only there will be no aliasing effect. So therefore I want to know what is the minimum sampling frequency, which is 2 times the FM max, which is 2 into 30, which is 60 kilohertz. So now I want to know what is the bit rate, means number of bits per second, means how many bits we are going to transfer in 1 second. So therefore the bit rate, the dimension of the bit rate is number of bits per second, and Fs is the sampling frequency. The unit is number of samples per second we are going to transmit, and n is the number of bits per sample. So for each sample how many bits we are going to, that is called as the n. So if you multiply n into Fs, so this sample get cancels, so therefore bits per second. So therefore the bit rate is equal to n into Fs. So bit rate is equal to n into Fs, where n is the number of bits per sample and Fs is the number of samples per second. So n and the number of bits is 3 and Fs is equal to 60 kilohertz, and if you multiply we are going to get 60 kilo bits per second, so BPS. So therefore this many number of bits we are going to transfer in 1 second. So through the output this many 80, so 180 kilobits we are going to transmit in only 1 second. So this is the correct solution of this question. So now we are going to solve the 120 question. See the question here. The quantization noise occurs in. So quantization noise is going to occur in only in PCM, pulse code modulation. So option C is the correct solution of this question. We have already discussed in the previous example itself. So quantization error or quantization noise is nothing but sample value minus quantized value. So because of using the quantizer in this block diagram of the PCM transmitter, this error is going to occur, which is the sample value minus quantized value. See, sample value can have infinite number of amplitudes, but here this quantizer is going to have a fixed number of fixed levels because of the we are going to use the number of bits. So we are going to convert the infinite number of amplitudes into a fixed number of amplitudes by using the quantizer. So therefore because of the quantizer in the PCM circuit only, we are going to get this quantization noise. So PCM, this quantizer is going to present in the PCM transmitter. So because of this only, the quantization noise is going to present in the, or quantization error is going to present in the pulse code modulation, which is a digital modulation scheme. So by this lecture, we have successfully completed the 120 questions, which are the previous year questions of the communication systems of ESE in a very, very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notifications comes from mobile. If any improvements in our video lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care, and bye bye.